All right, so we're recording this session now. This is a little bit of a test, but we're going to go over Lab 3, some of the common issues that you guys encountered in Lab 3 and that Megan sussed out as she was grading this. So I think the way we're going to work this is Megan will go over some general comments, and then I will chime in as necessary. So let's take it away.
Okay, so the first one, I was pretty happy with people getting the correct values on your Excel files for the most part. But the first little thing, and this isn't a wrong answer, it's just a clarification for question 5. I should have had it pulled up which lab question that corresponds to, but we're asking which age has the highest reproductive value? And then if you were to remove some of this population to translocate to another island in order to start a new population, why might you select individuals at this age? So a lot of you were right on point with choosing the year 1 had the highest reproductive value, and that's who you would want to choose because they have the ability to create the most offspring to start a new population. There's just one little caveat that we want to point out, and some of you may have seen this on the answer key, but posing the question, does that mean that you would want to move all of the year one age class over? And the answer is no. We just want to make sure that you don't remove all of that breeding population, because then you take away from the original population, which we didn't ask that in the question, so you didn't need to include that, but just something to keep in mind. You want to make sure that you're not taking away too much from the original one.
Right.
Question 6. I'll let Kevin kind of talk this one over, but it's asking if the vital rates in this population are density dependent. And this was one of the ones where a lot of people got it right, but then it kind of came up where, oh, we don't have enough information to determine if it's density dependent, or yes, it is density dependent. So I'll let you take this.
Good question. Yeah, this is a little bit of a trick question, but I just wanted to make sure you're thinking about density dependence, which is kind of a fundamental concept of all populations. That, you know, as you get more crowded, as there's fewer resources per individual, your vital rates might not go down. And, you know, as we talk about age-structured populations, we're getting into this new level of complexity where we think of, you know, different segments of the population differently, juveniles, adults, you know, we model them differently. But just be aware that as we start talking about this, we kind of stopped talking about density dependence for a little while. And so the answer is really no. I mean, there's no information about density dependence in a lot of these models, in a matrix model or a simple life table. There's no information at all. And so you're right. If you said, there's not enough information for me to say this population is or is not density dependent, that's the correct response, really. I just want to get you thinking about the fact that we added one level of complexity, age structure, and we took away another level of complexity, which is density dependence. And so I just want you to start thinking about that.
Excellent. So the next part, just a nice little overview for question 8, when they're asked to compare the 2 life tables of the pre and post reduction population of the squirrels. Maybe you could just give them like a general overview of the main difference, what you're trying to
Sure.
right there, because there's a lot of values. Everybody wanted to say, oh, well, pre and post, this is higher, that's higher, but what do those values actually mean?
All right, well, I'm going to share my screen for this. Megan, can you see my Excel?
Yes, I can.
Okay. So we have 2 different life tables here, a pre-reduction and post-reduction in density. And we can summarize, you know, all the basic statistics, the lifetime reproductive potential, the life expectancy, the generation time, little r. And the first thing that I would encourage you to notice if you look at these summary statistics is, first of all, that R0, the lifetime reproductive potential, is below 1 in the pre-reduction population, and it's well above 1 in the post-reduction population. So you see it's 0.92 pre-reduction and 1.6. Now that's critical there, because anything below 1 means you have a declining population. You're below replacement. Like, each individual can only replace itself by 0.92 pre-reduction, whereas each individual is more than replacing itself in the post-reduction. So that is also reflected in the little r. Now, little r, anything above 0 is going to be growing population, right? So this one is a growing population post-reduction, and anything below 0 is a declining population. So those are the kind of two things to really focus in on. That's a major difference. And so that's really what I was hoping you would focus in on. Anything else, Megan?
No, that was the main thing, just getting at explaining the conceptual meaning behind the values rather than just simply saying this is higher, that is higher.
Yeah.
Okay, so this next one is one that maybe we can try the whiteboard out on,
Okay.
or in Excel, I guess. But question 10, trying to simulate abundance of robins in the next year.
Yeah, maybe I'll go to Excel on this, because I think I need a little more practice on that whiteboard. That was pretty ugly when I tried to use it in our office hour early.
Well, it could have become one of those extra credit test questions of explain why this graph could look funky. What's going on with this population?
Yeah, so in this exercise, what we're doing is, and let's copy over these age classes. We're going to try to project out. And this is, let me move it down to the where it is down here. Okay, so, and this is meant as a segue into matrix population models to indicate how much easier it is to use matrix population models to project abundance of each stage from one year to the next, right? It's so easy. You can just do it in one line in R. It's much harder to think about this with a life table. And so this is really meant as a segue. So we're only going to do this once, and we're only do it for 1 year, right? So we're not projecting 20 years. That would be ridiculous for me to ask that. So what we start off with, as I recall, 0 that are 0 years old, 0 that are 1 year old, 10 that are 2 years old, 10 that are 3 years old, 10 that are 4 years old, and 0 that are 5 years old. I think that's the year 0 scenario. Or
yes.
And so then we want to project out to year 1, right? The easy part here is, well, these individuals that are year 2, if you increment 1 year, if you go forward 1 year in time, all those 10 individuals that survive would be age 3 next year. So that's great. So all we have to do is multiply those age 2 individuals by the survival rate of age 2 individuals, which is G sub X. So that's the survival rate from age 2 to age 3. We just perform that and we get 4. I mean, you could do that in your head too. We don't have to use Excel's equation editor, but I'm just using it. So now all the age 3 individuals, we just multiply them by their survival rate, which is G sub 0, which is 0.2. We're going to get 2 individuals that are now age 4. They were age 3. They survived. They became age 4. So that's easy. Now, how many are going to be age 5? Well, you could say just multiply all the age 4 individuals times the survival rate of age 4 individuals, which is 0. So you get nobody. And that's the easy part. And so then you have to think about, how is reproduction working here? Who's reproducing and when are they reproducing? Do they have to survive before they reproduce? And the way we've talked about these models, generally we say they need to survive and then they reproduce at the very end of the year, essentially, as according to the reproductive rate of that they associated with them in the following year. So that would be these age 2 individuals have to survive to be age 3, and then they reproduce as age 3 individuals, and they're producing individuals of what age? 0, because they're newborns. So here we could say, well, those age 3 individuals, those 4 age 3 individuals produce offspring at the rate of age 3 individuals here, which is 4.7, right? And then we add any reproduction from these 2 age 4 individuals. Those 2 produce 3.3 babies each, and we get 25.4 offspring in the next generation that are age 0. So I won't go through, there's another option here. You could have these individuals potentially reproduce first, and then those offspring have to survive. So another option here, I guess I will go through it because it's kind of useful. Another option here, this is year 1 alternate. Again, we're going to have 4 of age 3 and 2 age 3. So that won't change. That's fixed. But what we could say
you
is
made
those
that
individuals.
One a 3, just to let you know.
Oops,
right
I
there.
mistyped that. Yep, that should be 2. So that won't change. But, and here, let me just fill in the rest of that. So that's one correct answer. There's one more correct answer, and that is if we assume that reproduction hasn't taken place yet, and those age 2 individuals are going to still reproduce. They're just about to reproduce. And so if that is the case, those 10, there will be age 0 individuals in the population, because this is now this is pre-reproductive. So what we're saying is that those 10 individuals will reproduce. So I'll say, okay, what am I doing? Those 10 individuals will produce how many offspring per capita? 5.5, right? Because they're 2 years old. And these 10 individuals will produce 4.7 per capita. And these 10 individuals, because they're age 4, will produce 3.3 offspring. Now, that's great, but those offspring all now have to survive a year, right? So we have to we take all those offspring and we'll multiply it by the survival rate of 0 years olds. And that's 0.143 right there. So now we have 19 1-year-olds in the population next year, because they gave birth, and then all those newborns had to survive 1 year in order to get to the next stage. So there's 2 options here. These are both correct, and congratulations if you got either of those, because it's difficult.
Yeah.
Anything else, Megan?
No, I think that's that for that one.
We killed that one.
Yes.
I'm going to stop share there.
Okay. Let me take a look here. Okay. So the next question, you guys were asked to write out your equations in your Insight Maker models that model recruitment and mortality. And most of you did a really good job of trying to explain it in plain English. The one thing that I saw quite a few people make a mistake on, and we just, you have the right concept, but we just want to drive the point home. When we talk about, so this is for question 13, and it's asking, what is the equation for age 1 mortality? And then you're also asked to do the equation for age 3 mortality. And most people, you understand the concept. Age 3 individuals, they're all dying. That means that mortality is going to be 100% for this population. Where some people got this wrong in their equation, they said because it's 100% mortality, the equation just needs to be 1. But that is an egregious error because we still need to have the population size. Oh my gosh, that's terrible, Kevin. No. So we still need to have it multiplied by the number of individuals in the population. So instead of just 1, it needs to be 1 times your age 3. And a lot of you still kind of made that point when you explained it in plain English. So I tried to give you partial credit for that. But just remember, age 3 must still be in there for there to be a number to multiply your rate by. Boom. Let's see. I think the only other one that, sorry, I'm just going over these questions really fast. Question 18. A lot of people had the right idea here of what is causing this fluctuation. So, Kevin, maybe you can just kind of drive the point home a little bit.
Yeah, here, let me pull this up.
Difference between stochasticity and what causes fluctuations could look chaotic or stochastic.
All right, here, let me share my screen here. So if I simulate this, it really bounces around a lot at the beginning because you start way out of stable age distribution. You start off with 100 in age 1 and 0 in age 2 and 0 in age 3. But we're adding an additional effect here that if the population exceeds a certain level, then we, well, let's look at the equation because I already forget exactly how it works. But so if the population exceeds a threshold, every recruitment rate is reduced by 75%, or it's 25% of what it was if the population is below the threshold. So what happens then after the population exceeds the threshold? Well, you put it out of whack again. It's out of stable age again. So every time it's never going to settle in to smooth growth, because every time it exceeds a threshold, you undo the stable age, it's out of whack, and it's gonna maybe take a little while to get back into equilibrium, but you never give it a chance to get into stable stage, right? Because it's an increasing population, and it is going to exceed that threshold, and then you reset it and it's out of whack again. So it's never gonna be in whack, if that makes any sense. It's always going to exceed the threshold, and it's going to look weird. So it's going to look stochastic, but it's not. It's just bouncing around a lot because it's always out of stable age distribution. So does that make sense?
Yes, I think our key phrase that we're going for there's, if you go back to the simulation where you can show how it looks, it's being driven by the kind of the density dependence factor that was added. Is that kind of a correct?
Yeah. In fact, we could add the threshold in there, and
maybe the total.
Well, you'd have to add the total population on there too. So every time the total population exceeds the threshold, then all the vital rates, the recruitment rates go down dramatically, and that puts the population again out of stable age, and it's going to bounce around a little bit until the total abundance exceeds the threshold, in which case the whole thing starts over again. So you just can't get into stable age here.
Excellent. I believe that covers everything. I know we kind of took a little time, but anyone who wanted to get a little more clarification, I think this is helpful.
All right. Thanks, Megan.
Thank you.
All right. Oh, here, I'm just going to stop the recording.
Okay.
I was going to end the meeting. I was like, wait, I don't necessarily need to end the meeting.